right. So I thought I'd go ahead and work out an example of finding the area under a curve using the limit process. This is the example that we worked on in class. Here's our formula, which is basically the summation of some Riemann sums where this would be the height of each rectangle and this would be the width. And of course, we're going to try to get infinitely many of those rectangles. A couple of formulas that we need to take note of is that delta x is going to be the b minus a divided by n. And the general formula for c sub I is going to be a plus b minus a divided by n times I. Now the problem that we're doing here is a quadratic, so it doesn't really apply to this picture, but I thought I would just go ahead and work through the process of finding the answer using this limit process. So this is going to take a little bit of time, but if you're interested in seeing all the steps, here we go. So, so the first thing we want to do is we want to say basically that this area is going to be equal to the limit as n goes to infinity, the sum from I to, starting at 1 going to n, of f of, and now we got to figure out what is going to be our c sub I and our x, delta x. In fact, I'll start with the delta x. So notice here that we have a is 0 and b is 2. So that means I've got to do 2 minus 0 over n, or 2 over n. And then c sub I is going to be 0, that's the a value, plus, and then it's going to be the 2 over n again, and then I. In other words, it's just 2 over n I. So now I can literally plug that into our formula here, and I'll do that in blue. So this is going to be 2 over ni times, and then our delta x, and our delta x here is 2 over n. So the only thing I've done here is I've just done the initial substitution of the x sub I and the delta x. And so then let's go ahead and continue. So we're going to do the limit as n goes to infinity. I equaling 1 to n. Now our function is given right here, but I've got to plug that c sub I in for our x. So this is going to be 1/2 times 2 over ni squared plus 3 times 2 over n. So there's our formula with basically everything in it that we need, and we're going to have to work on this. The rest of this is going to be pretty algebraic. So let's go ahead and simplify this a little bit. N goes to infinity, summation I equals 1 to n. So then this is going to be 1/2 times, and then this is going to be 4 over n squared times I squared plus 3. So let's do a little bit more simplifying here. Limit as n goes to infinity. I equals 1 to n. And so this 2 and that 4 is going to cancel, so that's going to give us 2 over n squared I squared plus 3. Need a little bit more room down here. Whoops. All right, so let's go ahead and distribute the 2n. You do not have to do this. There's a couple of other little shortcuts that we can do, but I'm going to go ahead and distribute. So then 2 times 2, so I think that's going to be 4 over, then it'd be n squared times n, so that'd be n cubed, I squared plus, and then this would be 6 over n. So now we've got our summation here cleaned up quite a bit. Now I'm going to use the rule that I can break this summation of a sum into the sum of the summations. So this would be the limit of the sum of I going from 1 to n of 4 over n to the third. Oops, and then that's I squared plus, and then the summation I equaling 1 to n of 6 over n. And this is, oh, I guess I don't really need that. Let me undo this. This is, we're doing the limit of this whole thing. Okay. So all I did is I took this, the sum of this, the sum of this sum into the sum of the sums. Okay, and again, I'm trying to show every little step. Now what I'm going to do is I'm going to note that this is I, and then I'm going to, both sums are in terms of I. So anything that doesn't have an I can come out to the front. So this is going to be the limit as n goes to infinity of 4 over n cubed times the summation of I equaling 1 to n of I squared plus, and then this is going to be 6 over n because that does not involve I at all, going from 1 to n of, and then I'm just going to write the number 1 there. Now here's where we got to do a little side note. We have some sum formulas that I will mention now. I'm going to do them off to the side. So the sum from, that's a little bit bigger than what I would like to do. Let's get rid of that guy. Oops. Okay, let's go like that. So we need I squared and 1. So the first one I'm going to tell you is that I equaling 1 from n of a constant is simply c times n. So if that constant was 2, it'd be 2n. I'm going to skip one of the formulas and go to the other one that we need here, which is the summation of I squared. So this is going to be I equals 1 to n of I squared, which is going to be n plus 1, 2n plus 1, all of that divided by 6. These are in your book. You can find them in section 4.2. You could also Google them. Okay, so I'm going to use this formula here, and I'm going to use this formula here. So let's go ahead and scroll down a little bit more. And I'm going to go back to red. So this is going to be the limit as n goes to infinity of 4 over n cubed times, and now I'm going to grab that blue thing that I just wrote over here. So this is going to be n plus 1, 2n plus 1, all divided by 6, plus 6 over n times, and now I'm going to use the top formula here, which I'll scroll back up a little bit here, this guy right here. Now in this case, c is 1, so it's just going to be n. And, oops, I wanted that to be red, but that's okay. Now the good news is now we no longer have any summation formula or any summations. Now this is purely algebraic. I'm going to need to clean this guy up a little bit here. So let's see here. I need to take n squared plus n times 2n plus 1. So what I'm doing here is I'm basically multiplying this numerator out here. So I'm multiplying this, so that'd be n squared plus n, and then that'd be what, 2n squared, and then this would be plus, and then 2n to the third. And so when I add that together, I get 2n to the third plus 3n squared plus n. So that's another way of writing this. So I got the limit as n goes to infinity of 4 over n cubed times 2n cubed plus 3n squared plus n, all of that over 6 plus, and then that's just going to be 6. So that works out nicely. Okay, so let's just go ahead and make sure we don't make any careless mistakes here. Okay, first of all, I think I could make this become a 2 and that become a 3 by dividing both of those by 2. And so then that's going to make this denominator, if you will, is going to be 3n cubed. The numerator is going to be 4n cubed plus 6n squared plus 2n plus 6. And now we can go ahead and simplify that, just do some division. So this is going to be the limit as n goes to infinity. Well, that's going to be 4/3 plus 2 over n plus 2 over 3n squared plus 6. All right, we're getting there. Now, I'm going to break these into individual limits. We do the limit as n goes to infinity of 4/3 plus the limit as n goes to infinity of 2 over n plus the limit as n goes to infinity of 2 over 3n squared plus the limit as n goes to infinity of 6. Now, you could kind of skip this step, but I just want to make this clear. So what is the limit as we take a constant? Well, that's just 4/3. This limit as n goes to infinity, that would be 0 because the denominator is going to infinity. Same thing with the next term. The last term is going to be 6. And so you get a final answer of 7 1/3. So that would be the exact area, a little bit of work, of this parabola from 0 to 2. That exact area is 7 over 3.